what I have been told already, it is about TA, right? I had a talk about TA. So this TA and T1 are said to be equal in proportion. That is 265.4 Kelvin, right? And then 265.4 Kelvin. And then what we have to do is we have to just note down this temperature rise through compressor, and then we have this T1 value. Now from this T1 value, we are going to estimate the equation here, because you know the velocity, right? So velocity of the compressor. So what is the velocity of air at the compressor entry? It was C1, right? So here it is not C2, it is C1 square, right? So it is C1 square by 2 Cp, and for this T1 is already find out. Okay, 265.4 plus what is your C1? So C1 is 90 square divided by 2 into Cp. So Cp is 1.005, right? Just you substitute, instead of 1.005, substitute 1005, right? And then find the value of T01. Find the value of T01 and tell me the answer. Okay, students who are having a calculator in your hand, you can just operate it and find the value of T01 and tell me the answer. Yes, it was 269.4 Kelvin. Yes, it was 269.4 Kelvin, right? And then now you can substitute all the values, right, in this equation. You know the compressor ratio now, right? Compressor efficiency now. So what is your compressor efficiency? 0.79, right? So 0.79 multiplied by what? This T02 minus T01, that was 230 degrees Celsius. So 230, and then T01 is there. Here T01 is given in Kelvin, right? So what do you have to do? You have to convert this into degree Celsius. So in this, so divided by 269.4, right? And then you have to convert this in Kelvin. So what is in Kelvin now? It is 230. So 230 plus 273 gives what? 503, right? So how many? 503 kelvins, right? Equal to, and here minus 1 is there, right? So replace this minus 1 into plus 1, and finally we have R0C equal to the power of, what is gamma minus 1 by gamma? Gamma minus 1 by gamma is 0.4 by 1.4, right? So now you have to find the value of R0C. So R0C, you will obtain some answer, and then you have to take the power of 1.4 by 0.4, and you will get the value of compressor efficiency. Tell me the answer, please. It was 19.61. Whether it is R0C or only this value. This value is 19.61 or this 19. So R0C. R0C value is 19.61. Right? Huge compressor ratio. Right? So we are getting the compressor pressure ratio in this form. Right? And then we had solved for these facts, right? The pressure ratio developed by the compressor, that is B, has been finished, right? Now you are going for part 3. What is that? Power required by the compressor per unit flow rate, right? So per unit flow rate of air means you have to multiply with m dot, right? That is, you have enthalpy equation, you have to multiply the enthalpy equation with mass flow rate, right? So mass flow rate of the air, right? So here per mass flow rate, they have mentioned about unit mass flow rate, right? So you can avoid the value of m dot, and then you can find only the work done of the compressor, right? So finally we are going to compute work done of the compressor, right? You are leaving m dot a, and then you are multiplying with Cp multiplied by T02 minus T02, right? And then what is your Cp value? It was 1005, and then what is the change in temperature? It was 503 Kelvin, right? So into 503. So what is your answer? What is WAC now? What is WAC now? 505.5 kilowatts, right? So 505.5 kilowatts, right? So kilowatts per kg per second, right? So they were asking that per unit mass flow rate, so that kg per second, right? So this is the work done on the compressor. So we have finally finished the C part, and finally we are going for D part. So what is the D part? Explains that is the air standard efficiency of the engine, right? You have to find the air standard efficiency of the engine, right? What is the formula for air standard efficiency? Right? This is the formula. The formula for air standard efficiency. This is the formula. So neta J, right? Neta J is equal to 1 minus 1 by R to the power of gamma minus 1 by gamma. Right? So we are going to find air standard efficiency now. Neta J is equal to 1 minus 1 divided by R naught C whole to the power of gamma minus 1 divided by gamma. So 1 minus 1 by your R naught C is 19.61, right? So it is 19.61 whole to the power of 0.4 by 1.4. Now what is your neta J? Students, you can reply me in the chat box. Only Sebastian and Bagrit were answering. Need responses from other students also. If they are really evaluating, you can text the answers. So 0.57. Very good. So it is 0.57. That is 57%. Right? The efficiency is of the jet engine is 57%. Right? So these kind of problems will be asked in your examination part, and then these problems are continuously asked in your assignment questions also, right? So get ready with this thing in the assignments, right? Next thing, we are moving on to next thing, thrust and propeller thrust, right? We are going to deal about propeller thrust now. So what is meant by propeller thrust? What is thrust? Okay, thrust is the forward motion or forward force, right? The propulsive force which helps the aircraft to move forward. Okay, thrust is nothing but it is a propulsive force that helps to move the aircraft forward. Okay, that is called as thrust. And then what is meant by propeller thrust? You are producing the thrust with the help of propeller. Okay, then the thrust is called as propeller thrust. So this is the one-dimensional model. Okay, we are considering here Just a second, please. Sorry for the interruption, students. It's my neighbor's pet condition, right? Okay, let's see, right? Uh, we are considering two cases, that is fluid at rest, which is said to be the outside part of the duct of the jet engine, and then fluid in motion, which is said to be the inner part of the jet engine. So all the fluids are going, okay, that is all the fluids are going inside, means that is this propellers which is rotating will create the pressure differences, right? So the kinetic energy of the engine is getting improved, right? When kinetic energy of the engine is improved by rotation of the propeller, okay, what we experience is that we really develop the pressure differences. So that pressure differences brings you all the air inside the fluid in motion, right? And then we are having this phenomenon, that is here C1 and C2. So we are considering two facts, that is C1 and C2, right? And then we are considering the pressure at the inlet as ambient pressure, that is PA, and the outlet pressure as ambient pressure PA, right? And then when propeller is rotating, okay, we are having this convergence section. So in this convergence section, okay, the velocity is attained at the exit, right? The thing is, the inlet velocity is minimum and the exit velocity is maximum, right? So when inlet velocity and exit velocity is said to be both are equal, then we are obtaining zero thrust, right? So this is the condition of zero thrust, and this is the hypothetical case, and it is not going to achieve in any kind of jet engines. So in actual case, there won't be a zero thrust. So this is the hypothetical case. So we are not going to obtain zero thrust, right? So this is the working principle of the propeller engine, right? So in this propeller engine, what I am going to do is I am going to solve the first equation, right? So basically, I am going to solve for momentum equation, right? So what is your momentum equation? So force F is equal to ma. So mass into acceleration. But here we are considering the mass flow rate, right? So you are going to multiply mass flow rate with velocity, right? So mass flow rate with velocity, that is momentum. So mass flow rate of air with respect to velocity. So m dot a into C2, that is exit, minus m dot a into C1. So as far I told you, inflow, right? So inflow, in left hand side we are having the inflow, and in right hand side we are having the outflow, right? Outflow and then inflow, right? While solving one dimensional form of continuity, when we are solving the one dimensional form of momentum equation, okay, you have to consider this inflow and outflow condition. So inflow is negative and outflow is positive. So your outflow momentum is m dot a into C2, and your inflow momentum is m dot a into C1, right? So on taking m dot a out, what we get? C2 minus C1, right? So we have got m dot a into C2 minus C1, right? So what is C2 now? So C2 is nothing but Cj. C2 is nothing but Cj, that is jet velocity, right? And then what is C1? C1 is nothing but U. U is nothing but flight speed or flight velocity. So your jet velocity and then flight velocity. Okay, you are considering this as jet velocity and flight velocity, and your expression of thrust becomes, propeller thrust becomes m dot a times Cj minus u, right? Cj minus u, and then we are considering the speed ratio, right? So that is effective speed ratio. Effective speed ratio as sigma. So what is it? It is nothing but flight speed by jet speed, right? Flight speed by jet speed is called as sigma. Now I am going to write this thrust equation in terms of this speed ratio. So if we take out Cj common outside, okay, we get 1 minus u by Cj. Okay, what is u by Cj? It is sigma. So m dot a Cj 1 minus sigma, right? One kind of equation. From this you can develop the non-dimensional form, that is f dot f by m dot a Cj is equal to 1 minus sigma, right? And also we can rewrite this equation as m dot a, and you are taking common u, right? On taking common u outside, what do you get? So we get Cj by u minus 1, right? It is nothing but m dot a u 1 by sigma minus 1, right? And then we can write the thrust equation in non-dimensional form as f divided by m dot a into u is equal to 1 by sigma minus 1, right? So these two cases are the non-dimensional form of thrust equation, right? So thrust by mass flow rate into velocity. Okay, we are getting 1 minus sigma, and then thrust by mass flow rate into velocity, and we are getting 1 by sigma minus 1, right? So this is the thrust equation we are going to written in non-dimensional form, right? And then the other case is, okay, we can also have this non-dimensional form and its numbering system, okay, on the whole, with the help of this speed ratio. And when you are considering this speed ratio is equal to 1, when sigma is equal to 1, then what happens to this thrust? So f by m dot a Cj becomes 0, f by m dot a u also becomes 0, right? So this is the case. So this is the case of obtaining the propeller thrust, right? I think you could understand this better now, right? What is meant by thrust, and then what is meant by zero thrust. So zero thrust is that it is the hypothetical case. So when sigma is equal to 1, obviously we are getting thrust is equal to 0, right? And this is the called as the different kind of hypothetical one. And then in order to achieve the highest thrust, that is maximum thrust, okay, what is the condition is that we have to increase, or you have to match the exit pressure with the ambient pressure. When the exit pressure, if suppose this C2, here the exit pressure is said to be PE, means that exit pressure should match us with the ambient pressure. On that time we will getting the fully expanded work, okay. So fully expanded work has been done, that is fully expanded thrust would be obtained, right? So this is the other case. And then we have sigma is equal to 1, that is zero thrust, that is the hypothetical case, which does not exist in actual form, okay. In actual form, where the propeller is getting rotated, so what happens, we are having the jet velocity Cj as a maximum, not as a minimum, right? But the case is we are considering the infinite model. So this is the infinitesimal model. So infinitesimal sea air model, right? So in this infinitesimal sea air model, we are getting this zero thrust, right? In actual propeller engines or in actual propeller, the propeller thrust is not zero, right? It is always said to be the positive value, right? Next we are going to discuss about thrust, that is the same thrust in jet thrust, right? So I am considering a jet engine here, right? And this jet engine is said to be in one-dimensional form, where you are choosing a control surface and you are keeping the jet engine inside the control surface. The area of control surface is A1 and A2. See, the area of entrance of the control surface is A1 and the area of the exit of the compressor exit of the engine is said to be A2, and both the areas are same, they are equal. That is A1 is equal to A2, right? And now we are going to calculate the thrust of this particular jet thrust. That is, what is jet thrust? So jet thrust is nothing but momentum thrust plus pressure thrust, right? So F momentum plus F pressure. Initially we are going to find F momentum. How we are going to find F momentum? It's not the challenging one. So from the figure itself we could able to answer it. So it's a simple case that we can answer it very simple in for F momentum, right? So for F momentum, I am going to consider the same momentum equation that is we had discussed in our first class, right? Three-dimensional momentum equation in integral form. I am going to consider the same one here, and I am going to find the momentum thrust. So before going to that, I have to explain about this model first of all. So we have two different kinds of flow. One is internal flow and the external flow, right? So in this internal flow, the variation of velocity is said to be differed in internal flow as well as in external flow, right? Because the external flow velocity is mu, both in the entrance as well as the exit, right? So it is always said to be u. That is, external flow velocity is u, and that is said to be the flight speed, right? And then we have the exit velocity CE here. That speed is different, right? So exit velocity speed is different, and external flow velocity, that is flight speed, is different. So two velocity variation fields are there now, right? So you have to bypass. That is, we have to move the overall control volume of the internal flow control volume in the forward direction in order to attain the thrust. So this is the simplified case or simplified problem. And then for this internal flow, my jet engine is having the inlet area AA, and my exit area is AJ, right? So we have AE, and we have to find out the F momentum, right? It's very simple that we could calculate the value of F momentum via integral form, right? So it's that first of all I'm going to consider the inlet area, right? So the inlet area integral over AI, and then we have the density value as rho, and then your inlet velocity is u. Okay, so that is u square, rho u square dA, right? So I have just represent this inlet area alone, right? So in inlet area in integral form, I am going to write it the momentum equation only. This momentum equation is based on your three-dimensional momentum equation. That is three-dimensional momentum equation in integral form we had already written. I have considered the same thing only, right? That is, I mean that you already know this, right? So rho v vector, another time v vector into ds, right? I have used this formula only, right? So rho v vector dot v vector, right, into ds. So this v and v becomes v square, and then ds becomes dA, right? And this s is nothing but surface integral over area. So this area integral over area AA has been kept. Right? So I'm going to do the step for the other cases, right? So if you are considering it as an inlet area, then it is AA. Okay, and then you are also considering the other case, right? Integral over A1, right? So, since we have the external flow, no. So A1 and then rho U square dA, right? And then minus of here, this A1 is moving from 1 to I. So 1 to I, right? So when it moves from 1 to I, okay, this momentum is said to be in negative form since it is inflow. Okay, since we have inflow, that is A 1 to I is there, right? And similarly, this AI is also inflow, so you are going to add negative sign here, right? And then we have outflow. So where is our outflow? That is C. Now we are going for outside section, right? That is your outlet section is said to be positive, okay, which is the integral over A. So A, where the flow occurs from where E to 2 or 2 to E, right? So 2 to exit. So when we consider that 2 to exit, okay, it becomes plus, and then rho, what is this exit velocity at this 2 to E, that is rho C square dA. Okay, and similarly you are considering only for exit area alone. Okay, we have rho C square dA, right? So what is this? That is integral over 1 to I rho U square dA minus of plus integral over A 2 to E. So A 1 to I and then 2 to E, right? We have rho C square dA. So these two momentum, okay, becomes 0, right? So these two momentum is getting 0, right? And then here it is not a C square because here we have the exit velocity moves from 2 to E, means only U is there. In the A2, the velocity is U, so that we are having U, right? So A1 minus E, we are having one value, and then on substituting all these values, okay, by neutral, since the area in the A1 is equal to A2, that is entrance area and exit area both are said to be equal, and these terms is getting neglected. So finally we are having only these two terms, that is rho C square dA minus of rho U square dA, right? So therefore what is your F momentum? F momentum is equal to AE rho C square dA minus AI rho U square dA, right? So with this we can integrate this equation, and finally we can write it as rho C square AE, and then this is rho U square AI, right? So your thrust, momentum thrust will be in one dimensional form. After integration we get rho C square AE minus rho U square AE, right? So this is your momentum equation, and then my continuity equation, rho AV. So rho AV equal to mass flow. So what is your exit case now? So in my exit case it was rho CEAE, right? That is said to be the mass flow rate at the exit. Since in the jet engine we are considering two mass flow rate at the exit, that is mass flow rate of air plus mass flow rate of fuel, because inside the jet engine you are going to spray the fuel where all the fuel is getting burned, and then mass flow rate of fuel is getting added up where heat is released, right? So finally what is your mass flow rate? That is mass flow rate of air plus mass flow rate of fuel, right? That is rho A, rho C AE, right? And similarly, what will be the exit mass flow rate? Inlet mass flow rate. Inlet mass flow rate is rho U AI. That is your mass flow rate of air only at the inlet. At the exit, we have mass flow rate of air plus fuel, right? So this is the case. And then you are going to substitute these two values in this momentum equation, right? So you are going to substitute 2 in 1, right? So on substituting 2 in 1, what we get? So F momentum is equal to m dot A E minus m dot A into E, mass flow rate of the fuel, right? Neglecting the mass flow rate of the fuel to 0, and you are writing the momentum thrust as m dot A into C minus E, right? It's a simple notation, right? Why you are avoiding mass flow rate of fuel is that the mass flow rate of fuel for jet engines is usually enormous, because for 1000 ounce of fuel, that is 1000 ounce of air has to be squeezed during takeoff. For that 1000 ounce of fuel, okay, how much fuel you are spending is that for 1000 ounce of air, okay, how much amount of fuel you yield is only 17 ounces. So 17 ounces, that is 17 ounces of fuel is required for 1000 ounces of air to be squeezed, and those air is giving some thrust, right? For producing the takeoff thrust, okay, 17 ounces of fuel is only consumed. So when you are going for fuel air ratio, it was fractionally called 0.017. So when it is 0.017, when you are rounding up to that nearest decimal value, then it becomes 0, right? So that you are neglecting the value of fuel flow rate here, right? I think you may get this, and then this is said to be the momentum thrust, right? Now you are going to find the pressure thrust, right? You are going to find the pressure thrust. So F pressure. So what is F pressure, right? You have the exit area and then inlet area, and you are going to do some manipulative operations here, and then you are going to work it out for all the cases, right? So when you are considering the exit pressure, we have exit pressure PE, and then we have exit area EE, right? So your forward pressure, exit pressure will be like PE and AE, right? So this is your pressure force, right? And then we are having the other case, like we are also care to worry about the ambient pressure, right? So since ambient pressure is located, and we are going to add this ambient pressure, right? And then we have the change in area of differences, right? So change in area of differences is nothing but, that is, we are considering area at inlet minus area at exit, right? So these are the area differences. And then finally, when you are going to inflow side, right, in inflow you are giving that minus of PA into A, right? So what will be our final answer, right? Now we are going to simplify this final thing, right? It's very simple that on simplifying this relation, and this PAA is getting cancelled, and finally we are having PAE, right, minus PAAE, right? So what is your F pressure? F pressure is nothing but, on taking out AE common outside, right, what we get? Exit pressure minus ambient pressure multiplied by exit area, right? So this is your Fp, right? So this is your pressure thrust. So finally, what is your total thrust? So total thrust of the jet engine is F momentum plus F pressure. So F momentum is m dot a P minus U plus pressure thrust. So P minus PA into E, right? So finally, this is going to be your pressure thrust, right? And you are again making this pressure thrust as an effective, right? Effective jet velocity, effective thrust. So effective jet thrust is nothing but m dot a equal to Cj minus U. The case is, I had been already told you that when PE is equal to PE, on the time your nozzle is fully expanded, right? And then your exit pressure matches with the ambient pressure. Then what happens? This pressure thrust becomes zero. When pressure thrust becomes zero, only momentum thrust is there, and then the exit velocity is said to be the effective jet velocity, right? So by this case, okay, the above equation becomes as m dot a into Cj minus, right? And here is also you can substitute the same non-dimensionality, and this thrust equation resembles the propeller thrust equation. See here, our propeller thrust equation is m dot a into Cj, that is m dot a into Cj minus U. The same thing we are obtaining here, but this Cj is nothing but effective jet velocity. So effective jet velocity minus flow speed, right? So this is said to be the thrust equation, right? I think you all understand this particular thing, right? If not understood, right, once again I will explain. If anybody having any doubts, you can clarify. You can respond me in the chat box. Okay. Anyone having doubts? No. Right. We will go next. Next, we are going to see about propulsive efficiency. So you need some power, right, in order to give the propulsion, give the propulsive power, right? So in order to give the propulsive power, you need some devices that is called the engine. So with the help of jet engine, you are attaining some thrust, right? So we have thrust power, and then we have fuel power, right? So what is meant by propulsive efficiency? Propulsive efficiency is nothing but the ratio of thrust power to the engine power, right? So your engine power is nothing but all the kinetic energies, okay? So all the gas molecules, okay, which is coming inside the engine is getting used up, and the kinetic energy is released from it, right? So the kinetic energy of the flow of gases is recorded. The kinetic energy of the flow of gases is nothing but half mv square. So instead of half mv square, instead of v square, we have the change in kinetic energy. So what is your exit velocity? That is Cj. And what is your inlet velocity? That is U. What will be the total kinetic energy? The net kinetic energy is nothing but half m dot Cj square minus half m dot U square. So it is given. That is called engine power, right? So engine power is the net power developed due to kinetic energy of flow of gases, right? And this is half m dot Cj square minus U square. And then what is propulsive efficiency now? So eta P is equal to thrust power by engine power, right? So what is your thrust power? It was F dot U divided by, and then half m dot Cj square minus U square. Okay, if it is going to be the jet engine, we are going to use the same thrust equation. If it is going to be the any kind of turboprop or turbo fan, okay, any kind of engines, we are going to use the same thrust equation. That is only this F. F is equal to m dot a into Cj minus, right? Let's we substitute this. So m dot a into, and this m dot a will be replaced as a simple m dot, right? So mass flow rate, net mass flow rate. So net mass flow rate into Cj minus u, okay, that is F, and then another term u is there, divided by half m dot. Okay, you can expand this a square minus b square into Cj plus u, and then Cj minus u, in order to cancel out the common terms, right? So finally you have 2u divided by Cj plus u. Now you are going to divide by u. So divide by u, you get Cj by u plus 1, right? So what will be the propulsive efficiency now? So 2 divided by 1 by sigma plus 1, right? On taking LCM, what we get? 2 sigma divided by sigma plus 1, right? So this is your propulsive efficiency. So this propulsive efficiency became 100% when sigma is equal to 1. When sigma is equal to 1, propulsive efficiency becomes 100%. Is it possible? No. Your jet engine thrust and jet velocity when matches, you will absolutely obtain zero thrust. So for zero thrust hypothetical case, you are attaining the maximum propulsive efficiency. The thing is, when you are going to increase the thrust power, when you are going to increase the thrust power, on the time your efficiency, propulsive efficiency will getting improved, right? So instead of developing or increasing the thrust power, okay, you are if you are not going to worry about the engine power, then it's get to be difficult to work. So this propulsive efficiency is meant for all the cases, right? So how much is the engine power required for producing the equal amount of thrust power? So the energy spent is the main case. So engine power is also the important thing. So you have to calculate the kinetic energy of flow of gases from the engine power, and then you have to estimate this propulsive efficiency, right? So this is called propulsive efficiency, and then these are the propulsive efficiency for different engines. So here we have turboprop, turbofan, and turbojet. So turbofan is said to be the having the propulsive efficiency with high flight speeds in between turboprop and the turbojet. See, you may see that. So turboprop engine is there. So turboprop engine produces low flight speed with high efficiency, with high propulsive efficiency will be attained by turboprop engine. And then compared to turbojet engine, okay, turbojet engine is having high speed but low propulsive efficiency. So in between turboprop and the turbojet, we are having the turbofan engine as giving the highest propulsive efficiency compared to turboprop and the turbojet, right? So the maximum propulsive efficiency, okay, literally in this figure, okay, we will attaining some factors like around 70% or 67%, right? If we talk about turbofan engine, it nowadays we are having from 70 to 72%, right? So that is going to be the propulsive efficiency of a turbofan engine, right? And then it's time up. Okay, I'm going to end the session.